exam 2. That is 228. There's only one topic on it, internal loads. And I'd be happy to answer as many questions related to that as people want. And then if we finish that, we'll go back to the practice problem we were working on. It wasn't even last class, it was the class before. So I'll remind you about that problem. But anybody have any questions related to the test?
Just how to solve function trapezoid then.
How to, the thing we were talking about? Okay, so if you have, so this mostly comes up in problems where you have the triangular load going this way. And let's say that this is 15,000 newtons per meter, and let's say that this is 3 meters, and this is 2 meters. So the first cut.
Question.
Yep.
If we're hinged at the right in this case,
Yes.
why wouldn't we just flip the whole thing and say, all right, I'm going to actually answer this question, right? We take this situation and flip
Right.
it completely over to make it easier.
That is a good thought. I probably am going to make you do one like this, make you work from the side that where you have to do a trapezoid. Like you saw in that one practice problem, I mean, what if you do it like that? Then you're stuck. You know, what if there's two of these facing the wrong direction? So I think you should understand how to do this. Also, like, it just gives you a little math practice, and that's good, you know? So, so yeah, that's a good thought. But I want you to understand how to do this too. So the first cut is going to be valid for x from 0 to 3. And you can see that in this cut, there aren't actually going to be any reaction loads, so we can just go straight to calculating the internal loads in the first cut without figuring out what these are. And so the cut is going to look something like this. So you have a triangular distributed load, a rectangular. We know that this point is 15,000. We have to figure out what this point is. Okay, so this we know, this we have to figure out. The way to represent this point, the way to calculate it, is think of the coordinate system here. And we're going to figure out the equation for this line in y equals mx plus b form, where m is the slope and b is the y-intercept. Okay, so how do we figure out the slope of that line? Well, we know it goes from 15,000 to 0. That gives you the rise, and the run is 5 meters, right? So the slope is rise over run, which is 0 minus 15,000 divided by 5. And so you get negative 3,000. We don't have to worry about units right now. Okay, so that's the slope. And now what's the y-intercept of this line? Yeah, right. It's just the y-intercept is the y value when x is equal to 0. So b is just equal to 15,000. And so the equation for the line is negative 3,000 x plus 15,000. And now notice that, so this is the equation of the line for whatever x, right? If x is equal to 0, it gives you 15,000. If it's equal to 1, it gives you minus 15,000, right? But since the way we're doing this expression, the x value is the one over here, and that's the value we're trying to calculate, this is actually a representation of the point at the right endpoint. So that's the value at the right endpoint for the horizontal location x. Okay, so now I'm going to represent the shape like this. This value is 15,000. This value is negative 3,000 x plus 15,000. The width of both the rectangle and the triangle is x. And so the area of the rectangle is the height of the rectangle, negative 3,000 x plus 15,000 times the width. And so just multiply through and you get your expression. And the area of the triangle is, well, what's the height of this triangle? It's 15,000 minus 3,000x plus 15,000. And so you end up with just 3,000x times the width divided by 2. And so those are the expressions for the point forces. You're going to have two different point forces. So you'll have a triangular distributed load that comes to, what's that, 1,500 x squared. And then due to the rectangle, you'll have negative 3,000 x squared plus 15,000 plus 15,000 x. Then you'll have t, v, and m. And the locations are so this distance is x over 3. This distance is x over 2. And this distance is x. And so that's everything you need to calculate, to do Newton's second law and to calculate the moments. Any other questions about that example or using this method? What? Yeah, just not in this cut, but in the next cut you will, yeah. This is the cut. Well, so the important points are here, here, and here. So we have one cut before the roller and one cut after the roller. Yep.
How come in like instead we ever have to do the trapezoid and kind of always can just do like find out the distributed load and we'll just use the area?
When you have to use the trapezoid?
Yeah, but instead I don't remember ever really using it. I remember it was uniform over the whole thing.
Well, in statics, yeah, I let people get away with just flipping it. Like, who mentioned that, Alex? Oh, yeah. So if you have this problem, what Dan said is, well, why not just pretend you're looking at it, just walk around to the other side, and then the problem is this. Yeah. And that short walk can save you a lot of algebra, you know. But yeah, they both have their pros and cons. But there are problems where you can't get away with this. So I want you to know how to do the trapezoid. Was it in this class that someone was saying I should? Okay, so there's the problem, but it still just touches at one point. Oh no! This distributed load. But it still just acts right here. You know how you find the area? You find the area of a star using Guyot's corollary to Stokes' theorem. And here is what this powerful corollary says. It says, if you, okay, I did invent this and did name it, but then I looked online and someone else had invented it and named it a couple hundred years ago or whatever. But for any so convex, concave, combination of those two, polygon, I guess now it has, yeah, now it has to be, because you asked this question. Represent the coordinates of each vertex going counterclockwise as xi, yi. Okay. So if you have an n vertex polygon, then it's going to go from x1, y1 up to xn, yn. Then the area is equal to 1/2 times the sum for I equals 1 to n minus 1 of I might get this wrong. Y I plus 1 xi minus yi xi plus 1. Isn't that cool? That simple sum. And notice that, like, numerically, like if you think of like a numerical approach, any, you can represent a smooth shape as just a polygon with very small increments between the, so you can get a really good approximation for any area this way, just with this simple formula. It's a 2-line computer program, calculates the area of any shape. So like if you found the coordinates of this, all the way around, plug in this formula, assuming that I wrote it right, 50% chance probably, it would give you the area of that.
So basically, it just figures out that there's a bunch of little triangles, more or less. Or how's that?
I never exactly got like a simple geometrical understanding of it. It comes from, remember, Stokes' theorem relates double integrals to single integrals. I believe it relates double area integrals to line integrals. And so you can use Stokes' theorem, just assuming that these are lines in between, and you get a telescoping series where all these terms cancel out and you get this really simple looking thing at the end. But yeah, I never exactly, as far as like a simple, it looks so simple, it seems like there must be a simple geometric understanding you can get, but I never figured out what it was. Anyways, that's cool. I don't care what you say. Any other questions about, well, anything about the test? The stuff for the test, distributed loads? Internal loads? Okay. So let's go back to the practice problem, the example problem we were working on. And it looked like this. So back to the example from last Friday, I think it must have been. The problem looked like this. You had a beam, a pin joint here, a roller at the midpoint, a mass of 500 kilograms, and a force over here of 40,000, negative 5,000. And so far, what we figured out is, so there's two cuts for x values between, and let's see, what was the length? The length was, okay, thank you. 1 meter, 1 meter. And so for x values from 0 to 1, we had t equals negative 40,000, v equals negative 2452.5x minus 5,000, and m equals negative 1226.25 x squared minus 5,000x. And then for x between 1 and 2, t is equal to negative 40,000, v is equal to negative 2452.5x plus 9905, and m is equal to negative 1226.25 x squared plus 9905x plus 14,905. So what we're trying to do is find the maximum absolute value of the normal stresses. And what's relevant for that is the tension, the internal tension, and that's just a value of negative 40,000 the whole way. And then for now, we're not worrying about the shear force because the shear force produces shear stresses. What we are worried about is the bending moment. And that looks like this. And that extreme value is negative 6226. Okay, so now we're going to calculate the stress. So the stresses that we're going to care about are going to be in the x direction. We're going to calculate this due to tension, and that's going to be the axial force over the cross-sectional area. And we're going to calculate the XX stress due to bending, and that's going to be negative my over I. Okay? And then we're going to have to think about it a little bit to see at what point we're going to analyze this. And remember that now a point is starting to be, so when we think of internal loads, we tend to think of each of these x values at a point. But remember that if you look at the beam, each of these x values is really a line, right? And then not only that, but if you look at it, if you look down the x-axis, each line on this picture is actually an area, right? So we have to figure out not only what x value to do this at, but we have to figure out where on that cross-sectional area to do it. Okay? Any questions about what I'm talking about there? So, well, let's think about that for a second. Where are our likely candidates? Well, most likely, you'd have to guess that it's going to be here, right? So guess that the max XX stress in absolute value is here. But just remember that our cross-sectional shape is this. And so we have infinitely many points on here that we have to distinguish between. Okay, well, let's first figure out what I is and calculate the area, and then we can go start to think about where on this shape to look. So calculating the area is easy. Second, you're going to calculate the areal moment of inertia. And before you can calculate the areal moment of inertia, you have to know where the neutral axis is. Okay? So you're going to have to calculate the centroid to figure out where the neutral axis is. Okay, so I'll write out the dimensions of this shape, and then just take a few minutes and calculate the area and the areal moment of inertia. So the cross-sectional shape has, it looks like, anyone have that right here? Is this 0.3? This is 0.02, so that's drawn way out of whack. Okay, so so all the thicknesses are 0.02. And then this is 0.3. Okay. So take a few minutes, calculate the moment of inertia and the area so we can do the normal stress due to tension.